In Physics 1, by the time we get to work and energy, most students start breathing a little bit of a sigh of relief. Energy is a very fundamental concept to all sciences, but it's also a scalar quantity. So a lot of our work with vectors is not going to apply. So we sort of have a little respite from some of the math-intensive work. So energy is about making things happen. As this pitcher gets ready to do work on the ball and give it kinetic energy. So we'll be identifying different kinds of energy and the transformations that happen. So in this situation, again, work is how energy enters or leaves the system. And that happens by exerting a force, but only the force that's has a component along the direction of displacement counts. So in this case, F times cosine theta is the component of the force that's along the displacement. When we multiply force times distance, the SI units, so we get our newtons times meters, which is equivalent to joules. And joules is the SI unit for energy. But it's a really small unit of energy. So we'll explore other units of energy as we work through tutorials. But in this situation, if you're wondering, here's a force, but this force is perpendicular to this displacement as the gentleman carries the groceries from left to right. And so this isn't actually doing any work. However, if the force is applied in lifting, then work is done. So there are many times when forces are exerted that don't actually do mechanical work. Gravity is often one of them because in a circular orbit, if the force is perpendicular to the velocity, then the velocity doesn't change. And so if the force is always perpendicular to the path, then no work is going to be done and the kinetic energy of the object won't change. We also need to be prepared to deal with forces that change. And the way to do that is to recognize the fact that if we plotted force as a function of displacement, that the area under the curve is going to have units of energy. So if we had a varying force, then what we could do is break that up into small segments and then essentially take an average of the force over small intervals. But we know this from calculus as being an integration. So work is how energy enters or leaves a system. Here's one way that work can cause a change in energy. That's by increasing the kinetic energy of something. So as our bus increases velocity, that happens because there's a force being exerted. And so the work done, that force over the distance, is going to be equal to the change in kinetic energy. That's the work energy principle. Same is true in using kinetic energy to do work. So we can have a transformation goes in the other direction. In this case, the hammer has kinetic energy, and the nail slows the hammer down as it gets pushed into the wood. So in this case, the kinetic energy became useful work. Potential energy is another really important conduit for storing energy. And it can happen either through gravity or it can also happen elastically. If it's gravity, the work done on lifting something is going to be mass times gravity, that's the force, times the displacement, which we would refer to as a change in height. So that's how work can become gravitational potential energy. And also, gravitational potential energy can become kinetic. So these all represent different energy transformations that are extremely useful. For elastic potential energy, we can utilize springs. And the classic model for a spring is done with Hooke's law, where the displacement is proportional to how much force you use, which means that if I want to compress the spring twice as much, I'm going to have to use twice as much force. And the minus sign indicates that the force the spring exerts is always opposite its displacement. So if we make the spring smaller, it wants to get bigger. If we make the spring longer, it wants to get smaller. Sometimes that's called a restoring force, and that'll be important later on. So if we plot use Hooke's law and plot the force that we exert on the spring as a function of distance, we can see it's a straight line. And the area under a straight line is a triangle. So the area for a triangle is 1/2 base times height. And if the base is this displacement, we'll call that x. And then the height would be k times x, but then 1/2 of that. And then when we multiply that out, that's 1/2 kx squared, with k having units of newtons per meter. And then once again, this yields units of joules. So this is the elastic potential energy. And again, elastic potential energy can become kinetic, or it can do useful work. In all these situations that we've talked about, the work done does not depend on the path. But with friction, it certainly does depend on the path. We take a longer route, then there's going to be more friction, and that'll take more work. So that's why friction is called a non-conservative force, because it depends on the path. So here's our list of conservative forces, and they're all our classic forces that act at a distance: gravitational force, electric force, and then of course elastic, which is a contact force, but nonetheless. So these are situations where energy is going to be conserved. So if I let gravity do work on an object, potential energy is going to become kinetic, and I won't be missing anything. But things like friction, air resistance, those would be non-conservative forces, and the energy lost is typically lost in the form of heat. So when forces are conservative, the change in kinetic plus the change in potential is equal to 0. And if it's not conservative, then that change typically, as we said, is going to be lost as heat. This is a really powerful problem-solving tool that will be highlighted in the tutorial. So if the total amount of energy is always the same, then when we take a look at points in between, then the sum of kinetic and potential energy is still going to be equal to whatever the total is. Lots of roller coaster questions, because in a roller coaster, work is done in dragging the coaster up to the top of some hill. And then at that point, the coaster is going to be allowed to roll. Roller coasters typically don't have little motors on their cars, so they completely rely on conservation of energy. And in that case, a change in height results into an increase or decrease in kinetic energy. And in some cases, there's enough kinetic energy to do loop. Pole vaulting, this is a quiz question, is another great example of conservation of energy. So how come a pole vaulter can go so much higher than someone who simply high jumps? They take their kinetic energy, and that's definitely part of it. But if you look at the kinetic energy and the resulting increase in potential energy, it's only about half of what it takes to clear the bar for an elite pole vaulter. The other energy comes from bending the pole, their upper body doing work to bend the pole, and then that energy catapults them further. Power is the last topic for this chapter, and that's the rate at which work is done. And not necessarily work is done, the rate at which energy is transformed from one system to another. So if we think about power, a lot of us think about cars, vehicles. A typical way of rating vehicles is how much time it takes them to go from 0 to 60. So the engine does work in accelerating the vehicle, and it takes the vehicle up to some speed, for instance, 60 miles an hour. And then that increase in kinetic energy divided by the time is a reflection of the power output. The SI units for power are joules per second. So when we divide joules by seconds, we get watts. And again, a watt is a very small unit of power. We'll explore other units too, like horsepower. Now, if we group the change in time with a different variable, for example, if work is of force times distance, if we group distance and time together, then we can see the power actually could be force and velocity as well. Great, and so here's our summary, and be sure to check out the tutorial that's posted, which involves a loop.